Okay, today's video or lecture, we're gonna continue the topic that we started before regarding the metal forming. We said that in the metal forming process, the objective is just to expose the material into a very high amount of force to bring the material to the plastic zone. So once we plastically deform the material, it means that the material will attain a permanent shape, change in the shape, and this is the objective of the metal forming process. So again, the objective is just to expose the material into a very high force to produce very high stresses that should be higher than the yield strength of the material. This why we agreed that we're gonna give Y to the yield strength or the yield stress of the material through and we have to expose the material into a stress level higher than the yield strength to bring the material to the plastic deformation. Once we move to the plastic deformation, the material will exhibit a permanent shape, change in the shape, and this will give us the final product according to the concept of the manufacturing process. But if the stress it is not higher than the yield strength, it means that this is a clear failure of the metal forming process. We didn't succeed to perform the metal forming process. So then we discussed the plasticity, since we are talking about the plastic and the elastic, so it was important to understand the difference between the stresses within the elastic region or the plastic region, and we consider to explain this thing is the simple tensile test. Like if you do have this bar and you stretch this bar with the original length L0, so due to exposing this one into a force, a tensile force, PI, I stands for instantaneous, like this is the instant, at this instant of time, this is the amount of force that already acting on this bar. So this bar will be stretched with a certain L, so it will attain another L, this is the new length, this is the instantaneous length of the bar. If we increase this force, this bar is going to increase further. As we decrease the force, so this one it would be decreasing, depending, right? So the basic idea that for every force, there is a corresponding value of the length as new length. So this is the instantaneous length and this is the instantaneous force. So if we did the tensile test, we shall end up with a typical shape or example of this stress strain curve. We do have the elastic region as usual, it is a straight line. In the plastic region, we do have this curved thing, and these are the equations that we discussed for the elastic region, and this is what we used to use for the mechanics of material class, but these are the new equations that we shall use in this course, since we're gonna move to the plastic zone. We said that the engineering stress, it is E times E, which is the uppercase E stands for the Young's modulus or elastic modulus of the material, which should be the slope of this curve, right? And or this line, and E, this is the engineering strain, which is Li, which is the instantaneous length negative L0 over L0. But in the plastic deformation, and this is the equation that we're gonna use, the true stress, we have to define the true stress. The true stress should be the instantaneous force divided by the instantaneous area. But the engineering stress is the instantaneous force over the original area. Right, this is what we used to do for the mechanics of material class, but this is the new form that we're gonna consider for the true stress. The true stress, in this course, we're gonna give it a name as flow stress. Why flow stress? The flow stress, this is the amount of stress needed to keep the material to be fluid. And this name of the true stress as a flow stress, it makes sense more to the metal forming part, because in metal forming we are exposing the material into a very high force, so the material should be fluid between the die or the object or the thing that you push the material with. And it's gonna be clear, for example, when we discuss the extrusion process. Through the extrusion process, we're already pushing the material to flow through a small channel, for example. So we need an amount of stress to enforce the material to flow. So that's why this type of stress is named as flow stress. This is the amount of stress needed to keep the material flowing under the action of a very high stresses in the plastic deformation, as plastic deformation. So whatever it is, true stress or flow stress, it is K times epsilon T power N. This is the bar law. This is commonly known, this bar law is commonly known as the simple power law, as we discussed. This simple power law it is very common for many of the material. Most of the material there, true stress or fluid stress, it is described by this simple bar law. And we said that this K, it is commonly known as the strength coefficient, and N, this is the strain hardening exponent. The true stress, which is epsilon T, which it should be different than the engineering strain. The true strain, it is the ln, the natural logarithmic of Li, the instantaneous length, over L0. And since we do have the volume is constant, which is this equation, like A0, L0, this is the cross-sectional area of the bar, L0, this is the original area, length, equal the instantaneous area time the instantaneous length. If we plug this data into these equations, here we gonna substitute for Li over L0, this is gonna give us A0 over AI, which is the original area over the instantaneous area of this bar. Right? We mentioned that the true stress is Bi over Ai, which is the instantaneous load over the instantaneous area, and this is the yield strength. In the elastic region, this yield strength, because it is a common point, you should understand that this point, it is like common point between the elastic region and the plastic region, right? So it means that if we decided to calculate the yield strength, and this is important, notice, if we decided to calculate the yield strength based on the equations of the elasticity, we shall end up with the same results, the same yield strength if we decided to calculate it, but based on the plasticity. Why? Because this point, it should be like a common point between the elastic and the plastic region, right? So it means that if I decided to calculate Y, which is the yield strength, according to this equation, because this is the stress, how it would be related to the strain. So let us assume that the strain at this point, this is the yield strength. This is the yield strain of the material. This is the strain at the yield point. The strain at the yield point, it should equal to the strain, the true strain at the yield point. So this is the engineering strain. This is the true strain at the same point. They should be the same values. Why? Because we already sticking at the same point still. The corresponding value of the stress, it should be the yield strength of the material. So Y, which is the yield stress of the material, it should be E times EY. EY, this is the yield engineering strain of the material. This is if we decided to calculate the yield strength from this equation. If we decided to work in the plasticity, it should equal to Ky epsilon Y power N, where K, it should be the strength constant, this N, it should be the strain hardening exponent, and epsilon Y, this should be the true strain at this yield point. This true strain at the yield, it should equal to the natural logarithmic of the new length of the bar at the yield point divided by the L0. If we stretch, if we knew how much is the force needed to bring this bar to the yield, and we subject this bar to this force as By, so we're going to end up with Ly. This is the length at the yield point. If we divided this length by L0 and we took the natural logarithmic to this fraction, we shall end up with the yield strain, the true strain at the yield point. Plug it here, you're going to end up with the yield strength, which should give us the same value if we calculated the yield strength using this E times EY. EY, this is the engineering strain. At the yield point, it should be equal to the Ly negative L0 over L0. Make sense? We said that also we discussed the effect of the temperature, and we said that when we as we increase the temperature, the strain hardening exponent, which is N, is going to decrease. The strength of the material is going to decrease. And we said that at very high temperature, this N, it would be intensively decreasing, will become very small, tends to zero. And it doesn't make sense anymore to use this equation. Or in other words, if we use the equation of the simple bar law, the K epsilon power N, if we use this equation to describe the fluid stress or the true stress of the material at high temperature, it is not accurate. Why? Because this N decreasing intensively tends to zero as we decrease the temperature of the material. So, and we mentioned that as we increase the temperature, the deformation of the material, the plastic deformation of the material depends more on the strain rate. So that's why this equation is recommended for the flue stress. What is the flue stress? This is the true stress as we mentioned above. So to calculate the flue stress at high temperature, it is recommended to use this equation more than the simple bar load that already given up there. Make sense? What is this C? This is known as the strength constant. The strength coefficient is K. The strength constant, this is C. Epsilon dot, this is the strain rate. The strain rate, it should be strain over time. So its unit, the strain has no unit. It is dimensionless. T, it should be in seconds. So the unit of the strain rate, it is second power to the -1 or 1 over second. It should equal to V over Li if we are doing tensile test. Like if we're already having this bar and we're stretching this bar with a force, and this force it shall be moved with a velocity V. So this is the speed by which we're already stretching the bar itself. So this will result in some strain rate. The strain rate, it should equal to the V over the instantaneous length, the new length of the bar. But the engineering strain rate, it should be this engineering strain divided by time, which should be equivalent to the V, which is the velocity of stretching the bar over the original length. So all the time in the engineering side, we're already referring to the original area, original length, but here we are referring to the instantaneous area as we discussed the previous meeting. Make sense? So all of these parts, we already covered them. It is highly important to acknowledge the difference between the two cases and to acknowledge or to know that we have to work in the plasticity. We have to bring the material to the plasticity to have a successful metal forming process. Make sense? Now let us move to this term, a new term here, which is the average flue stress. What is the average flue stress? It is some of the operations. This is going to be clear as we discuss the different metal forming process. We do have so many different types and methods of metal forming. The common between all of these methods that we have to expose the material into a very high force to produce very high stress. So we do have some operation like rolling, forging, and so on. So we're going to discuss these operations. Some of these operations, the way by which changing the material, it depends on the flue stress. But some other operations depends on the average of the flue stress, not something that we call as average flue stress. This is the thing that I'm going to discuss now. So for example, what is the average flue stress? If we are exposing the material into a stress level that is higher than the yield strength, so we shall be moving into this point, for example. Like assume that this is the YF, this is the instant, this is the true stress at this instant. So we shall end up with a certain deformation of the material. This deformation will be, as we agreed that this, when we remove the load, we're gonna return back parallel to the elastic region because of the spring back effect as we discussed the previous meeting. So this is like a stress level and this is the yield strength. Some of the metal forming processes, its deformation, it should be described using the flue stress. And some other operation, its deformation, it should be described by the average between the flue stress and the yield strength of the material. Like you're already taking average between these two values. You got my point? So this average here, it should be the average flue stress. We're gonna give it a symbol as YF bar. Bar stands for the average, YF stands for the flue stress. So this is the average flue stress of the material. So again, why we need this term? As I mentioned, some of the metal forming processes to describe how the material is going to deform, how the material is going to plastically deform, to change the shape using this method of metal forming. To describe this material deformation, you should use the average flue stress. But some other operation, you should use the flue stress. Like for example, stretching a bar. You'd have this bar and you are going to change the shape, the length of this bar. This is a metal forming process. The stretch of the bar to the plastic deformation, to describe this thing, to describe how the material is going to deform, you have to use the flue stress only. There is no need for the average flue stress in the tensile test. But for example, in the rolling operation, as I'm going to explain to you, in the rolling operation, to describe how the rolling operation, it can be done, we have to use the average flue stress. Okay, so that's why the average flue stress is another measure that is important for the metal forming process. So that's why it is important to understand what is the average flue stress. So how we can calculate this average flue stress? Simply the general formula of the average flue stress, Y average, Y F bar. We can write this one like Y average, for example. But let us use this representation of the average flue stress. It should equal to the 1 over epsilon times the integration from 0 to epsilon to the flue stress d epsilon. This is the general formula of the average flue stress. Like you, as I mentioned, like you already taking the average of the flue stress needed to bring the material to a certain strain rate. So you're already doing integration over epsilon, so that's why you have to divide by epsilon here to take an average. Like you already count and divide by the number. You got my point? So what is the average flue stress according to the, let us work according to the simple Bauer law. According to the simple Bauer law, what should be the flue stress? Should be K epsilon bar N, right? So if you plug this one here and did the integration, this should give us the Y average, the average flue stress 1 over epsilon, the integration from 0 to epsilon to the flue stress, right? How much is the flue stress? It is the, according to the simple Bauer law, this is the flue stress, so it should be K epsilon bar N d epsilon equals. If we did the integration, so 1 over epsilon, remember that this epsilon, this is the true strain. It is not needed all the time to type T since we are using. So from now on, we won't gonna type T, we won't gonna use the subscript T. Why? Because this only the equation that we have to use. All of these equations on the right, these are the equations that we shall use through this course. So there is no need to type all the time T. T stands for true, and epsilon, we are pretty sure that we have to use the true strain measure. So that's why I removed the T here. So this epsilon, this is the true strain, or this is the targeted strain. You could consider like, assume that you do have a material and you have to deform the material plastically to change its shape, changing the shape or to attain a new strain. So you have, this is the target strain. This is the strain that we have to achieve by exposing the material into a very high force. Okay. So carry on. If we do have this 1 over epsilon just constant outside the integration, if we did the integration, K just constant, right? The integration of this one N is just exponent, so we're gonna add N plus 1 and divide over the new exponent, which is N plus 1. You got it? Like the integration, because we're already integrating over epsilon. So K just constant, epsilon bar N. Integration of this term is gonna give us epsilon N plus 1, because we have to add one more to the exponent and divide over the new exponent, right? Which is N plus 1. Then we can cancel this epsilon with the 1, because this is epsilon. If you just combine this epsilon bar N plus 1 with the epsilon, so we have to subtract -1, so this one will be cancelled, right? So this is gonna give us at the end the average flue stress according to the simple Bauer law. This is the average flue stress according to the simple Bauer law. It should be K times epsilon, or we can write this one as K epsilon bar N over N plus 1. Make sense? So this is the average flue stress, how it looks like in terms of the strength coefficient, the strain hardening exponent N, and the true strain, how it would be related to the true strain. But this is the original formula, this is the original equation. This equation is a special one. This is just, this one just when the YF, it is calculated using this equation. But if the flue stress, it will be described by a different equation, this equation is not valid anymore. You have to use this one, this formula. Make sense? So the average flue stress, this is the general formula. This is just for the simple Bauer law. The simple Bauer law, the flue stress, it can be represented as K epsilon bar to N. If we did the integration, we're gonna end up with this formula. We can even write this one, if you can observe. What is K epsilon bar to N? It should be YF, according to this assumption, the simple bar law. So we can write this one, the average flue stress, we can write it as the flue stress over N plus 1. But it is not all the time with this form. This is just in case that we're already working as using the simple bar law for the flue stress. Make sense? Also, if you remember that we said that the flue stress, which is YF, it would be represented as C epsilon dot bar to N, or it would be represented as K epsilon bar to N. Both are simple bar laws, but one that depends on the true strain and the other one depends on the true strain rate. Okay? When we shall use this one, we have to use this one. It is recommended to use this formula when we're already working at elevated temperature. We said that most of the metal forming process are done at high temperatures. At very high temperature, it is recommended to use the strain rate because the deformation of the material depends on its strain rate. So, since we have two possibilities for this YF, we can generally write the average flue stress as YF over N plus 1, which would be K epsilon bar N over N plus 1. If we're already working at room temperature or a little bit higher temperature, it means that still the deformation of the material depends on its true strain. Or in case that at very high temperatures, it is recommended to use this formula as C epsilon dot power M over N plus 1. So this should be N still, not M. You got my point? Because the thing that should be changing only the numerator. The denominator all the time it is N plus 1 as long as we already defining the average flue stress based on the simple power law. Make sense? So this is gonna give us the general form of the average flue stress and how it would be related to the flue stress of the material. As I mentioned, why we are introducing this average flue stress? Because we need it in some of the operations to accurately describe its mechanics. Mechanics, it means that how the material in this manufacturing process is going to change in the plastic zone. We have to use the average flue stress for some operations. Some other operations, we're going to use the flue stress. So that's why it is important to know how we can calculate these two terms for different materials. Make sense? Again, this is the average flue stress according to the simple bar law. If there is another formula for the average flue stress, which is different than this one, we have to use the general integral form. We have to do the integration from scratch. But for this average flue stress, if we're already working as simple bar law, so there is no need to do the integration. You can directly use this equation. Make sense so far? So let us continue. Let us consider this examples on these equations and formulas and things that we already discussed up there. So the focus in this fundamental part of the metal forming, we're gonna consider that our main metal forming process is the simple tensile test. Like we're already having a bar, this bar, and this bar is going to be stretched by a force, with a force. Okay? So for this operation, we are originally we are intended to change the length from one value to the other value. And this point is very important. Why? For example, in this operation in the bar, we already stretching the bar to increase the length with the tendency to increase the length because the length is too lengthy in comparison to the thickness or to the width or the diameter of the bar. The length is too lengthy, right? So why I'm telling you these things? Because when we are going to define the true stress for a tensile test bar under tension, it should be defined at the length of the things that we mean or we want originally to change to this material. What is the objective of this metal forming process? The objective of this process is to change the length from L0 to Li, which is instantaneous to new length. So that's why the true strain it should be the Li over L0. Someone would say, okay, and in the meanwhile for this operation, when we stretch the bar, when the bar is stretched, what should happen to the diameter? The diameter should be decreasing, right? The diameter is going to decrease. So we had like D0, this D0 will be decreasing to D. In the meanwhile, we do have L0 and it's going to change to L. So the question is it possible to define the true strain as ln D over D0 or D0 over D? For the tensile test bar, no, it is not possible. Why? Because if you remember, we defined the true strain. We defined the true strain as ln L over, it should be L over L0. Li over L0, right? This, yeah, if the volume is constant, this term, okay, let me write this one down here. If the volume is constant, epsilon T, as we define it, it should be L over L0, right? If we decided to work, if substitute with the diameter, the volume is constant, so this should give us the A0 over AR, the instantaneous area, right? And the area of the bar with a circular diameter, it should be ln pi over 4 d0 square over pi over 4 d square, right? So if we cancel the pi over 4 with the pi over 4, this is going to give us the d0 square over d square. You got my point? So if we decided to work with the diameter, we have to consider the squares. But here for the lengths, we have to consider the lengths itself. There is no squares. So in example 1, it is mentioned that the strength coefficient. What is the strength coefficient? This is K. And the strain hardening exponent, which is N, of a certain test metal are given by K and N. So this is the K and N value already given to us for this material. Remember that N and K, they are mainly material dependence. But in the meanwhile, they do depend on the temperature. As we increasing the temperature, both are decreasing. But assume that at a certain temperature level for this material, K with 40,000 pound over inch square, which is PSI. This is in the inch system. And the strain hardening exponent is 0.19 and it is dimensionless. A slender specimen. So the specimen is cylindrical shape of metal with a starting diameter. So this should be D0. So this is the first given data here. D0 is already given by 2.5 inches. And length, so this is the original length, it is 3 inches. Is compressed, we are going to compress the material, compress to another length. So the objective is to change the length, whatever by tension or compression, but the objective, the main objective of this operation is changing the length from 3 inches to 1.5 inches. Make sense? So we are going to decrease the length to, this is the instantaneous length, the new length. It became 1.5 inches. Determine what is required, the flue stress. What is the flue stress? It is required to find, these are the requirements. The flue stress, which is YF. At this compressed length and the average flue stress, how much is the average flue stress? So the average flue stress, which is Y average, how much it is? These are the requirements. Did he mention which law that you have to use for the flue stress or the average flue stress? No. So directly, we're gonna use the simple bar law. The simple bar law that is state. So the first thing, for the flue stress, let us calculate the flue stress, which is YF. Okay? The flue stress, which is YF, according to the simple bar law, it should be K epsilon bar to N, right? This is the one that we have to use. Since he didn't give us any flue stress, if the flue stress function or equation is not given to you, so you're gonna directly use the simple bar law. Make sense? This is the simple bar law that we already using. So how much is K? K is already, to calculate the flux stress, we have to calculate the strain first, right? The true strain. The true strain should be length, the things that are going to change. We are going to change the length from 3 inches to 1.5 inch. So it should be Li over L0 or L0 over Li. But directly make the higher value on the top to end up with a positive value directly. So don't bother yourself with the sign. So the true strain, it should equal to the length of the instantaneous length. It is 1.5 over 3. So we can put it like 1.5 over 3 equals, if we did the calculations, 1.5 over 3 and the natural logarithm of half, this is going to give us the negative 0.693. This negative here indicates that the length is going to decrease. And this makes sense. So that's why the original form of the natural logarithmic equation of the epsilon, it should be ln the new length over the original length. This is the original form. But as I told you, in case that you messed it up or just put the L0 on the top and Li in the denominator, it doesn't matter. You're going to end up with the value. And the thing that we are interested in is just the value. Okay, so this is the true strain. Plug it here, you're gonna end up with the flux stress. The K is already given by 40,000. The epsilon is 0.693 power to the N, which is already given. N is already given by 0.19. So it's gonna be 0.19. Doing the calculation, you're gonna end up with something. Use the same unit. Add the K. The K is already given by pound over inches square, which is PSI, so it should be the same unit. This is equivalent to the PSI. So if we did the calculations, power to the 0.19, power 0.19 times the 40,000, this is gonna give us 307.7 psi. So this is the flux stress. This is the first requirement. The second requirement, the average flux stress. Flux stress. The average flux stress according to the simple bar law. If we're already using the simple bar law, the average flux stress, it should equal to the flux stress over n plus 1, which is K epsilon bar n over n plus 1. We already calculated the flux stress by this value. So it's going to be the 307.77 divided by n that we already got it by, that already given by 0.19. So it's going to be 1 n plus 1. If we did the calculations, we shall end up with the average flux stress. Very simple. 31, 35, 1 psi. And that's it. So these are the requirements for this example. Make sense? So it is very simple example for using or calculating the flux stress based on the simple bar law. Any questions so far? So let us consider this example of a tensile test. So since the talk is about a tensile test, it means again that the objective is to increase the length. Tensile, it means that we are going to increase the length. This is the main objective of this operation, is carried out to determine the strength constant. We are interested in calculating the strength constant, which is C. In this equation, the flux stress, it is C epsilon dot bar to M. Okay? And the strain rate sensitivity exponent, which is M, it is required to calculate C and M. This C and M for this material. For certain metal at 1000 degrees Fahrenheit or at a certain temperature level. At a strain rate, this is the strain rate. What is the strain rate? It is, so these are the given data. At strain rate, this is the strain rate 1. The first strain rate that is already given equals 10 over second. Because we said that the strain rate, it is a strain which is dimensionless over time. So the unit, it should be 1 over second or second inverse. You got my point? Like we can write this one like S negative 1. This is the first strain rate. When we subjected the material into this strain rate and we measured the stress, which is the flue stress, we measured the flue stress, we got it by 23,000 pound over inch square. Then if we repeated the process but at higher strain rate, if we increase the strain rate, this is the second strain rate, at 3,000 second negative 1, we get another flue stress. We measured the flue stress again, which we observed that it had been increased to the 45 pound over inch square. So the question is, how much is C, how much is M given this data? Right. One of the things, experimentally speaking, like what we explained for the simple power law. So the flue stress is C epsilon dot power M, right? If I ask you to find the log of this equation, to write the log equation, the log form of this equation, as we did for the K epsilon M in the previous meeting. So this one, if we already have here, so this is the solution of, so we already have the flue stress, it should be C epsilon dot power M, right? If I ask you to write this one in the log form, so this is gonna give us the log of the YF, the flue stress, equals the log of C plus the M, the log of epsilon dot. Agree? So this will be converted into like a linear function, and if we decided to plot the log of epsilon dot over the horizontal axis and the log of the sigma, or the log of the flue stress, the log of the flue stress over the vertical axis, we shall end up with a straight line because there is a linear function, right? And the amount of, at the instant that this log, when log epsilon dot equals 1, this shall give us C, the time constant, the strength constant of the material. Because if this log equals 1, I'm sorry, equals, the log itself, it should be 0. When epsilon dot equals 1, it's gonna give us this, the C value, right? And the slope of this line, the slope of this line should give us M. Make sense? The slope of this line, it should give us M. So let us calculate M first. Let us calculate M first. How we can calculate M? Your objective is just to find the log of, just to end up with this log equation. And you're going to end up with the slope. Okay? So simply, if you calculate the log of this epsilon 1, so let us calculate the log of epsilon 1 dot equals, this log is going to give us 1. And its corresponding value of the log YF equals, calculate the log of this value, which is the log of 23,000. This is going to give us the 4.36, right? And also calculate the second data, which is log epsilon 2 dot equals, this is going to be the log of 300 gives 2.4, gives 2.477. And this corresponds to log of the YF, which it should equal to the log of the 45,000. This is going to give us 4.65. All right? So simply, it means that we're already having two points. Like we do have 1 point, which is 1, log, the log epsilon equals 1. This corresponds to a certain value, which is 4.36. And when this one is, it became the 2.477, we end up with this value as 4.65, right? So what should be M? So simply using these two data, these 2 points, we can set up this triangular shape to end up with this slope. So the slope is going to be the difference, this like delta y, and this is like delta x, right? So simply, we can calculate M as the difference between the log of the C over the log of the tan inverse. I'm sorry, it should be the tan inverse of the log YF to negative the log of YF1 divided by the log of epsilon 2 dot negative the log of epsilon 1 dot. Just the difference. I don't give care to the, I'm sorry, it should be, there is no tan. Okay? If we did calculations, what? Yeah, you can directly plug into this power law equation, okay? But I want to let you know how we can experimentally determine this M using these two data. This is basically what we are doing in the experiment, okay? So if we calculated this difference, negative 4.36 divided by the difference between these two logs, which is just 2.44477 negative 1, this is going to give us the 0.198. This is going to be the M value. Then once you got the M, you can plug this M, use this M with one of these two data to end up with the C. So for example, the first one, we got the flue stress, which is 23,000. It should equal to C epsilon dot that correspond to this value just 10. So this is going to give us 10 to the power of 0.18. If we did the calculation, we shall end up with a value for this C. So this is going to give us 10 to the power of 0.198 and divided by 23,000 to the power 1. This is going to give us 14578. So this is going to give us the C. Okay? Make sense? So the last example here of an aluminum alloy is used in a process in which the effective strain is given by this value. What is the effective strain? This is the targeted strain. This is the strain that we would like to achieve, right? Like the material initially with no forces, we have to expose this material into a force to achieve a strain or strain the material to this level. This is the effective strain that we would like to achieve. This effective strain, this is the true strain that we're gonna work. This is the true strain. This is like the true strain that is already given by 0.4. Make sense? If the initial yield stress, which is the yield strength of the material, is 100 megapascal. So we agreed that we define the yield strength as 100 megapascal. This is the yield strength, which is Y. We agreed to give Y uppercase to refer to the yield strength of the material. It is required to determine a suitable value for the yield strain, epsilon 0, in this equation. So what is this epsilon 0? This is the yield strain. So the yield strain, he gave it a name as epsilon 0. So how much is epsilon 0 within this equation? What is this equation? This is not like the usual simple bar law. It is a simple bar, it is a bar law, but it is not the simple one because we already including this steps epsilon 0 already here. So how we can calculate this epsilon 0? How much its value? To this flue stress, this is gonna change only epsilon. But how about if we made this flue stress equals Y? YF equals Y at this instant, this epsilon should be epsilon 0. So considering this fact, we can calculate the flue stress is already given by 100, right? The yield strength is given by 100 megapascal equals K, which is given by 500 mega times epsilon 0. Epsilon 0, we have no clue how much it is. It is required to calculate epsilon 0. But when the flue stress equals the yield strength of the material, this epsilon should be epsilon 0. Power to the n, which is already 0.26. So we're going to end up with one equation and one unknown only, which is epsilon 0. We can simply calculate how much it is. Okay? This is for for point A. For point B, compare the stress given by this law and the stress obtained by the simple bar law at the final strain. يعني لما نوصل للstrain ده, when we achieve this strain, how much is the stress, which means the flow stress, and compare this one by the simple bar law flow stress. So if we calculated the flow stress using this formula, which is K times epsilon 0 plus epsilon power to N. Epsilon 0, this value, it won't gonna change. This value is the same value. You already got it here, plug it here. K is already 500. This epsilon is given by 0.4, N is given by 0.26. You can calculate the value of this flow stress in megapascal. So this is the flow stress according to this formula. How about the flow stress according to the simple bar law? It is K epsilon power N. This is according to the simple bar law. K is already 500. The epsilon is 0.4. N is 0.26. You're gonna end up with another value. Compare between them. See which one is bigger than the other. This is for the requirement B. For the requirement C, it is required to compare the average flow stress based on this law and the average flow stress obtained by the simple bar law. So how much is the average flow stress by this equation? The average flow stress, it should equal to the 1 over epsilon, the integration from 0 to epsilon, the flow stress d epsilon. Why we are using this formula? Because this is not the simple bar law. We are changing the formula, so we have to use the integral form for the calculation of the average flow stress. This is going to give us 1 over epsilon, the integration from 0 to epsilon, the flow stress, which is K, times epsilon 0 plus epsilon power to N d epsilon. Then do the integration. If we did the integration, this is going to give us the 1 over epsilon, the K bar epsilon 0 bar N plus 1 divided by N plus 1, right? So this is going to give us the flow stress, the average flow stress. Then you are going to substitute for epsilon with 0.4. N is given by 0.26. And this is 0.4. And this is, we got it as we got it before. And this is 500. So we're going to end up with value in megapascal for the average flow stress. Go ahead and compare this one to the average flow stress from the simple bar law. The average flow stress from the simple bar law is K epsilon power N divided by N plus 1. K, it is already given 500, epsilon is 0.4, N it is 0.26 over 1 plus 0.26. Do the calculations, you're gonna end up with something in megapascal.